this computer. It's a multi-part question. Share screen. Okay, so we're here. I've got an extra day. I'm going to spend the entire day on dynamic logic, which is good because it confuses people. And then I'll spend a whole day on flip-flops, which is also good because those also confuse people. Wow, I'm impressed. Makes me think I screwed something up later on down the line. Homework 3 is due on Thursday. Lab 2 pre-lab's due on Friday. We'll finish lab 2 in 1 week. I will be in lab, but not until 1:30. Sean will be manning Zoom and Max will be in the room until at least, and Sean can be there at least until I get there. I think he can stay the whole day that time. Next week, we're going to review for exam 1 on Tuesday, and we will take exam 1 in person in EGR 234 on Thursday, February 11th. If you cannot come for the exam in person, email me this week and let me know, and I will set up an appointment for you to take it remotely. And please do it this week, otherwise I go crazy because it's confusing enough trying to manage this. If I feel like semi-organized where I have a list of people, I feel a little bit better. I shouldn't tell you this. I had a freshman last semester, who decided that for some reason he thought the exam was like it was a Monday, Wednesday class, and he thought the exam was on Thursday. And so he shows up on Thursday and he says, well, where, in the classroom? And this is like, and then comes to my office and he goes, when's the exam? And I said, yesterday. And I actually let him take it when, I don't know why, just because he was a freshman. I know, I should have just swatted him right then. Okay. Lab 3 is a 2-week lab, and you will have to write an actual lab report for that. There is a highly detailed rubric, highly non-detailed rubric on View and Learn. I'll tell you more about the details later. Okay, the body effect is always important. As long as you know what the body voltage is, you compare it to the source voltage, it will first order affect what your threshold voltage is, which affects the current, which affects the speed, which affects everything. If you don't tie the body down, what happens is the body floats. And this is, well, maybe this would be better for the other class. So when you get into the lab and you have these 4 terminal transistors that you're building yourself, when you start building schematics yourself, this is an NMOS transistor. Let's look and see what happens. It's built in a P substrate, and it's got these N+ diffusions for the source and the drain. These are diodes right here. I have a PN junction diode. If I let the P float, if I let the body float, this thing's going to conduct current, and it's going to conduct a relatively large amount of current, could destroy your device. If you do something like this, and it's an imager chip where this P substrate is exposed to light, this happened. This is a true story. This P substrate is exposed to light. The photons entering the P substrate get converted to electrons, and they force current to flow and wreak havoc, and you actually accidentally build an imager. And yeah, I had to write a paper on that device. And I was the scapegoat, because I was the youngest one, who had to present the paper at the conference. Everybody else just sent the chip back to NASA and said it's a POS, we don't want to touch it. I was told I was paid for 6 months of testing. I was going to do 6 months of testing, and I figured out what was going on. I'm presenting this paper. And there's this guy in the back of the room, and he is really excited by my paper. And I just like want to crawl under the desk. And he's asking me all these questions and everything. I'm just like, go away. And we get down to the end. They said, no, it's time. You guys go out in the hallway, find a room or something. Just, just talk. And he was trying to build an imager by burying photodiodes in the substrate. No one had ever done this before. 5 months later, they've got a patent on it. And it's the patent on the camera that the basic technology for the cameras that everybody's using right now. He took his money, and I know this story because I ended up working for him a few years later. He ended up taking his money and is making movies in Bollywood. And I'm at NAU. Okay. Life is strange these ways. So anyways, be careful when you get those 4-terminal transistors. You do have to tie the bodies. On NMOS devices, the bodies go to ground. You just tie all the bodies to ground. Otherwise, you have imagers. Boy, that was a weird chip. PMOS, you tie the bodies to VDD. And that's so you reverse bias those PN junctions so current cannot flow through them. Okay. We looked at a few temperature effects. We found that K prime goes up with temperature, V threshold goes down. Net effect is you get more current as temperature increases. And we talked about thermal runaway a little bit. You'll hear a lot more about that when you actually start working. No, we're not on capacitance. Why are these slides in here? Am I? Oh.
You did the 3 hours slide. We were just about to get into dynamic. Yeah.
We're in O2. I know. I had a few review slides in here, but okay, we'll just run with this. Oh no, whatever I clicked. Just go. Ed! Oh, just go away. Okay. Aren't you glad you can see everything on my screen? PowerPoint is what I'm looking for. Okay, so we talked about this. I must not have saved this in the right place. We talked about this. Okay, so we looked at last class, in 280, we started looking at the static CMOS. This is the standard pull up and pull down where the NMOS transistors in the bottom are ORs and the NMOS in series are ANDs and in parallel are ORs. We looked at transmission gate logic. There'll be one static CMOS problem on the exam. There'll be one CMOS pass transistor on the exam. Today we're going to look at dynamic logic. And just a quick review of CMOS pass transistor, because this is the first time we looked at this. Single transistor implements the AND function. I put one signal on the drain, one signal on the gate. If the gate is true, because it's NMOS, and A is true, I will get a 1 on the output. So this is A and C. If either A or C is low, if C is low, the gate turns off and nothing gets through, it's an open circuit. If A is low, then a 0 goes to the output. So one transistor for the AND function. I just simply wire them together. It's called a wired OR. X or Y, I tie them two together. The one that, if one of them has charge on it, has a voltage, it will drive the output high. Wow, that's simple. Except for the Shannon thing. Okay. This is right. Okay. We want to look at dynamic circuits. Let's start with what I have on the slide. With static logic, every node has a low resistance path to VDD or ground at all times. With pass transistor logic, we have to ensure this criteria using something I call the Shannon criteria. And basically, we have to make sure that there's a low resistance path to VDD or ground at all times. We have to add extra transistors. And that was the point of like most of last class. Static logic is just great. There's no floating nodes. It's guaranteed every time. You have to deal with those PMOS transistors, which are big because of the N-wells. And they're larger transistors. They have a bigger W over L to make up for the fact that they're slower. So they have a higher capacitance. This is something Colt Morris wanted to do every time he came into class. With dynamic logic, what I'm going to do is I'm going to get rid of the PMOS pull-up network, and I'm going to replace it with a single transistor. I'm going to use the charge stored on the output capacitance to hold the state high. And then I'm going to clock it and evaluate it. So the signal's only going to be good for half a clock cycle. Yeah, there's all kinds of things going on. This node, this output node is floating half the time. It's floating a quarter of the time. And it's going to get some noise and pickup, but I can decrease the size of my logic circuits and squeeze them maybe into a smaller space if that's necessary. First thing we want to do is we want to talk about capacitors. Oh, yay. I get to do this right. So for capacitors, Q equals CV. The amount of charge stored equals the capacitance times the voltage. The way I do this, if I have a positive voltage at the top of this capacitor, that means positive charge is stored on the positive voltage side and negative charge is stored on the negative voltage side. Passive sign convention rules, current goes into the positive terminal for electrical engineers. Now, a couple of equations for capacitors that I always keep in mind. I equals CD VDT. That just always is on the top of my head. But remember, current is also the rate of flow of charge. It's dQ dt. So if I have current flowing, I have charge moving. Charge moving means that the voltage on this capacitor is changing. I get a dV dt when I have a dQ dt. Now let's look at that capacitor. I'm going to erase a bunch of those arrows at this point. Charge is being removed from the top plate. So if charge is moving from the top plate, it's got to be going up this way. Positive charge flow is electrical engineering current flow. So if charge is moving off this plate, dQ dt is going up, dV dt is also changing. This is a negative sign on here because it's moving away from the capacitor, so the voltage is going to go down. When I remove charge, the voltage goes down because the capacitance is constant. E drops. I is negative in this case because it's going against the direction of passive sign convention. It's flowing up to get the positive charge moving up and away from that plate on the capacitor. Okay, capacitor review. Don't worry, there's buckets of water involved. You've been to my classes before. You know there's buckets of water involved. Okay. This is dynamic logic. And what I've done here is I put this transistor up here and I put an extra transistor down here, and I use the same pull down network that I used in static CMOS. So we can remember that static CMOS, or standard, whichever word I use that day, is inverting. When I build the logic function with a pull down network, I'm going to get the NOT of that. This dynamic logic is also inverting. The pass transistor that we looked at yesterday, and this is, people get confused with this, the pass transistor is non-inverting. I see a lot of logical errors on the exam based on that. So this one is inverting just like standard CMOS. What I've done is I've taken the pull down network and I've replaced it with QP and Q, whatever that says, QE. Now, how do I make this thing work? Oh, if I wanted to build a function here, so we look at this circuit right here, I can evaluate the function just like it was standard CMOS. I have A, it's in parallel with the series combination of B and C, so I get A or BC naught. Same type of logic function. But I've built this with 5 transistors. If I use standard CMOS, I'd get rid of these 2 transistors and I'd add the pull-up network. I would have 6 transistors. So I've saved a transistor. If I had a more complex logic function, I'd save more transistors. Because with standard CMOS, it's 2 times the number of literals, 2 times if I count the variables in the equation, standard CMOS takes 2 times that number of transistors. Dynamic logic takes 1 times the literals plus 2. So I can build a structure using fewer transistors, yes.
What are the 16 5
The 16, wait, what did you just say?
The writing there, 60.
6 transistors.
Oh, 6 transistors.
Yeah, five transistors versus 6 transistors. Yes.
And then what does the phi do again?
The phi is a new signal that I have to add to this circuit, and it's a clock. Okay. Now, the way this is basically going to work, I might as well just jump ahead, is I'm going to turn phi on. So I have 2 cycles of the clock. Here's phi. And let's just say phi starts out high, because that makes more sense. So if phi is high, this transistor, wait, no. If I wasn't planning on talking this much, if phi, I was going to race through this. If phi is low, so in this first half of the clock cycle, phi is 0, and it's 0 in both places. So if this is 0, I've turned on the PMOS transistor, and I've turned off the NMOS transistor. It doesn't matter what A, B, and C is. I have an off transistor in series with them. The PMOS transistor is on, Y is going to be high, no matter what. And not much of a logic gate. I always get a 1 out of it. It always works correctly. Then I'm going to go into the case, well, suddenly my clock goes high. When that clock goes high, this is going to go to 1. This transistor goes off. The bottom transistor goes on. Then it's going to be whatever this function is. It will only get pulled down if A or BC is true. Otherwise, I'm relying on the capacitance the load capacitance of this line to maintain a high voltage. So I've got to switch this clock fast enough that that capacitance doesn't discharge. And I have to, what else do I have to do? I have to, I've only got my logic function during half the clock. So it's only valid half the time. But I've saved a few transistors, and sometimes that's enough to make you a hero. Okay, so here we go. We got two cases here. Let's look at the first one. ABC is high, high, low. So A is high, B is high, and C is low. Okay. This transistor is going to be on, this one's going to be on, and this one's going to be off. Now we got two parts of time that we have to worry about. I don't know what's going on here because I have to know what was going on before. So that's a big X. That's unknown right now. When I go into the pre-charge phase, and this is another name of this logic, it's called dynamic logic. It's called pre-charge and evaluate logic. It's called domino logic. When I go through the pre-charge phase, I'm going to, that's pre-charge. I'm going to pull this one low and phi is low. So if this transistor is off, I have a short to VDD, my output's high, and it doesn't matter what A, B, and C are because I have this off transistor in series with them. Now I go into evaluate. I gotta change colors. So in evaluate, the clock goes high. My logic stays in the same place. Now I've turned this transistor off and I've turned this transistor on. Now I potentially have a short circuit between the output and ground. And let's see if I do. Yes, I do. I can go through transistor A, through transistor E, and get to ground. So my output will be pulled to 0. As soon as I pull pre-charge low again, the output's going to go back high. So my output is going to look like this. When pre-charge goes true, it's going to be high, and when evaluate's true, it goes low. And as soon as pre-charge goes low again, this is going to come back high. So this is the only time my signal is valid. My output is valid logic. So I lose the static part of the CMOS. I've got something that's only, and so I can only really look at that output and figure out what's going on with it when evaluate is high. What really happens is, since this one, let's say we got another case here. So if ABC was, let's go to green. ABC is low, low, high. Then low, I don't have a path in here to ground. So what would happen in that case is this would start out high. There'd be nothing to pull it down, so it should remain high. But in fact, we've got resistance and capacitance on the line. So there's a little bit of a droop here. And then it goes back up. And you have to design it so that the droop's not too big, or the clock is faster, to keep that all together. A lot more complicated, but again, you're trying to fit something into a smaller space. So you give up performance a little bit.
So if you have something that's edge sensitive reading from this, do you have to like make this clock read the normal clock, or?
You have to make sure that the evaluate cycle of the clock lines up when your actual whatever it's driving is critical. You could use it, you could latch it in on the evaluate or shortly after the evaluate. You almost need a separate clock. Yeah, you need separate timing on my clock. It's a mess. Not my favorite, but it gets used a lot. Okay, now we're going to look at a real circuit. Why am I doing this to you people? Okay, so here's one right here. Now this is another trick that people use, is I'm going to, since I can't rely on this just holding itself up, I'm going to put a standard CMOS inverter on the output. And that will hold it up much better than, you know, just storing it on this capacitor. Okay. What is the logic function of this circuit? Just think about it and write it down. Yeah, I'm going to give you a few seconds. I'm sorry. Good, at least I can see the look on some people's faces.
That's what I thought.
Okay. Right. Why did they do this? Why did they do this to poor little X1? You got 4 transistors in parallel. Okay. If I put 4 transistors in parallel, it has a W over L equivalent, since they add like capacitors, of 20 over 2. I've effectively made a larger transistor, but maybe I can fit that in a smaller space. Because if I have to make the W of the transistors bigger, I've got to make my standard cell smaller, it's taller. And I may not have room to do that, where it's easier to put 4 transistors in parallel. It's just a way of making bigger transistors and squeezing them into a smaller box. Okay. It's inverting these, effectively, I just have 3 transistors in series because this parallel network, the gates are all going to X1. Okay. We want to draw a dynamic logic circuit to implement this function. Did I really do this to myself? Let's just do this. Okay. I'll make it easier. Okay, I want to implement this function. The way I would do that, I need A, B, and C in series. I need that in parallel with D, E, and F. And I need that all in parallel with G. So we get something that looks like, oh no, 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 no. I'll be back. Yeah, I don't know. Press it hard or press it too fast. Give me 30 seconds, I'll be back. This is slide 15.